This is the ics321 screencast on normal forms part 2. Now again, recall redundancies in tables and how we address them by decomposing the table into smaller tables. For example, hourly employees gets decomposed into two smaller tables, pulling out the rating wages dependency. And recall that we want two properties of decompositions, one of them being lossless join. Lossless join saying that when you join the decomposed relations together, you should get back exactly your original relation. And again, recall also that if you have, for the case of decomposition into two tables, there is a very nice theorem that says that, well, it is guaranteed to be lossless join if you can show that the intersection of the decomposed tables is a key for either one of the tables. Now, what about the case of decomposing into more than two tables? Well, you can sort of apply the theorem recursively, but there is a very nice procedure called the Chase test that actually lets you determine if a decomposition is lossless join. So for example, if we have a table ABCD with attributes ABCD that's decomposed into three different tables, S1, S2, S3, S1 being AD, S2 is AC, and S3 being BCD. Now what we do is we construct what's called a tableau, which is a French word for a table. And the table that you construct is going to have one row for each of the decomposed relation. So we have here the table and the tableau actually. One row for each decomposed relation. So row 1 is for S1, row 2 for S2, row 3 for S3. Right? For each row, we subscript an attribute if it does not occur in Si. So in S1 we have A and D, but we do not have B and C, so we subscript B and C with 1. In S2 we have A and C but no B and D, so we subscript B and D. In S3 we're missing A, so we subscript A with 3. Now then we are going to use the FDs that were given to us for the relation R, A, B, C, D, and we are going to do some inferencing or some processing over this table, this tableau. Using the FDs, I'm going to try and equate two rows. Okay, and here are the rules you're going to do. If one row is unsubscripted, make the other the same. If both are subscripted, make the subscripts the same. The goal is to get one completely unsubscripted row. I know this is cryptic. Let me show you via an example. So if we now look at this tableau, right, nothing has been done yet. Now if I look at my FDs, I have A determine B. What does that mean? An FD says that if the values agree in A, then they must agree in B. So I have two values of A here, which are two small a's that are not subscripted. So they are the same. They're completely equal, and that means that the B values must be equal. So now I have to make the B values equal using the two rules here. Now if both are subscripted, I make the subscripts the same. So I change the second subscript to B1, okay, or to 1. Now again, I try to apply the FDs, right? I have B determines C, so I've got two B1s here that are the same, so the C values must be the same. Again, now in this case, one of them is unsubscripted, so we make the subscripted one unsubscripted. Now let's try and apply, what else can I apply? right? I can apply the third FD in this case because I have a CD here and I have a CD in the third row. And it says that, well, if these two agree, then the A have to agree. And again, I have one unsubscripted A, so I'm going to change this to unsubscripted. At this point, I've reached my goal. I've one unsubscripted row. And whenever that happens, this means that the decomposition is lossless join. If the decomposition is not lossless join, you'll come to a point where you get stuck and you cannot make progress anymore. Okay, and then the remaining whatever values you have in your tableau, that can be used as your counterexample. Okay, as we'll see in the exercises. Okay, now let's come and talk about the second property of decompositions that's desirable. A dependency-preserving decomposition. And the intuitive definition is this, is that if we decompose R into tables X, Y, and Z, and we want to enforce FDs that hold on X, and on Y, and on Z, then FDs that were given to hold on R must also hold, meaning that I do not need to do a join in order to enforce all my FDs. Now, to define this rigorously and mathematically, I need one more concept, which is the idea of projection of a set of FDs. Now, if R is decomposed into X, the projection of F onto X, denoted F subscript X, is the set of FDs U determine V in F plus, such that U and V are in X. Okay, this is not rocket science. This is just saying that only the FDs that contain the attributes in X can be in the projection. That's all this is saying. Again, this is an example here where in order to check the FD SC determines I do need to join the two relations together. I cannot check SC determine I by looking at the individual decomposed relation. So now we're ready to define dependency-preserving decomposition, right? A decomposition of R into X and Y is dependency-preserving if F subscript X means projection of F on X, union the projection of F on Y. Take the closure of that should be equivalent to the closure that you have for R. So if we consider only dependencies in the closure of F plus that can be checked in X without considering Y, and in Y without considering X, these imply all dependencies in F plus. Okay, so here's an example. ABC is decomposed into AB and BC. And the set of dependency F is A determines B, B determines C, C determines A. Is this dependency preserving? Can I check A determines B using the decomposed relations? Yes. Can I check B determines C from the decomposed relation? Yes. Can I check C determine A using the decomposed relations without a join? No, I couldn't. Okay, so this is not dependency preserving. Note that dependency preserving does not imply lossless join. They're two different concepts. Okay, so I'll leave you to figure that out on your own. Now, how do we decompose R into a set of smaller relations that are all in BCNF? Well, the intuition is quite simple. If an FD violates BCNF, pull that out into its own relation. Repeat until all relations are in BCNF. Okay, so for example, if you have a table ABCD and you have the if you have the FDs B determines C, C determines D, determines A. Well, first you got to find the key, and then after that you have to check which of these violate BCNF, and you start pulling them out into its own relation. Now note that the solution is not unique because it depends on the order in which you deal with the violating FDs. Okay. Now the book provides a very nice algorithm, and this algorithm is it's a sort of a detailed version of the intuition that I just told you, and you should look at what this does. Right? So whenever again you consider a violation and you compute the attribute closure of that, of the left hand side, right? And then you choose that as your decomposed relation, okay? And then you need to union X with whatever that's not in the you have to find the X is going to be the key, right, for R1, and then you're going to find R2, which is X union R minus X plus. Then you compute the FD projections, then you recursively decompose R1 and R2 and return the union of the results. Okay. Okay. If you use algorithm 3.20 to decompose your relations, it's guaranteed to be lossless join. But in general, there may not be a dependency-preserving decomposition into BCNF. And we've seen some examples before, like the student calls and instructor relation. But here we have another one: title, city, theater, with FDs, theater determines city, and title and city determines theater. This is not in BCNF, and you cannot compose this while preserving the second FD. And so this is the motivation for 3NF. Now, how do you decompose into 3NF? Okay, and you can actually modify the algorithm for BCNF decomposition and actually stop earlier. But how can we ensure dependency preservation? And here we have a problem. One approach is whenever an FD is not preserved, I'm going to add it back in. Okay, but then that FD may violate 3NF, so that could be a problem. I'm going to skip this example. So instead, we're going to use what's known as a minimal cover for F. And if we use a minimal cover, things will work out. So the minimal cover is really just the minimal set of FDs that's equivalent to the closure. And you normalize all FDs so that the right hand side is a single attribute, and you try to delete attributes from FDs such that the closure doesn't change. Okay, so intuitively the cover is as small as possible, and if we use the minimal cover, again, here's an algorithm to compute the minimal cover, which basically you put everything in standard form, you try to minimize the left hand side of each FDs, you delete any redundant FDs. Again, the answer is not unique. But the point is, now if you use the minimal cover and then you do the decomposition using the minimal cover, right, then you can actually get a 3NF decomposition that is dependency preserving. Okay, so what have we covered? We have covered functional dependency, we've covered normal forms. In particular, we've covered BCNF, and that if a relation is BCNF, it is free of redundancies that can be detected using FDs, right? Thus, trying to ensure that relations are in BCNF is a good idea in general. Now, if a relation is not in BCNF, we can try to decompose it into a collection of BCNF relations. But we have to consider whether it's lossless join, whether FDs are preserved. In general, we do want lossless join and dependency preserving decompositions. Now, you should always consider other requirements like performance when you do decompositions.